AC power. Whereas Edison in New York was having to put DC booster stations every like 10 blocks, something like that in the city. So what Tesla did is, because of voltage drop, and what Tesla did is he gave it AC over a huge long distance and then just stepped it down to whatever voltage that was needed in the area. This problem with AC because of the changing field, we know that there's eddy currents and hysteresis, and the effective resistance goes up. They say that it also causes problems with, if it's underwater, let's say in Georgia Strait, you've got a high voltage cable going from Tsawwassen to Victoria. It's actually DC. They say the AC is going to kill fish or something. I'm not sure. There's all kinds of reasons. You can look. I'm seriously. You can look into it. Yeah. So in certain instances, they'll use high voltage DC, but then they'll have to change it into AC so you can transform it again. Transformer only works on AC. It has to have a changing current through those windings, right? Anyway, so that's that point there. That's one of the big ones. Transformer, wait a minute, change the magnitude of transformer to transfers to transformers can change the magnitude of resistance, inductance, capacitance. I don't know what they mean by that. Is that a new point in the book? Anyway, the main ones, step up, isolate, and safe transmission. Well, this might be something to do with loading up a circuit. Okay, so these 1, 3, and 4 are probably the main categories. Mutual induction. So if I have a wire or a circuit, it produces your left-hand rule, the one with the fingers and the thumb, so hitchhike, left-hand rule. Which way is the current going when the field is going in that direction on the left? Current.
Counterclockwise.
Up. Current's going up, right? Okay, it's producing that field. And the current is still going up, isn't it here? What's the difference then between the left diagram and the right diagram? If the current's still traveling in an upwards direction, from negative being here, or counterclockwise, you could say, through the circuit, what's the difference between both of those diagrams?
Size increasing, one's decreasing.
Right. One is an increasing amount of current flow, and the other one is a decreasing amount in the same direction, just smaller. So it's collapsing the flux lines. So even though they're set up in the same direction, it's collapsing. And then when it flips around the other way and it'll expand again, these arrows will be going in the opposite direction. The flux arrows. Because the current then would be going down. AC supply. So because AC has a continuously changing field, we know this. We have self-induction going on in the wire, and it's generating a voltage or a counter EMF, but it's not very significant. Not with a piece of wire. But if you put it into a coil, you know that intensifies those flux lines even more. And so then you get reactance. So if this was coil, right, then you'd get a lot of kickback, back EMF or counter EMF, so that it limits the current through that device. So that's how the primary of a transformer works. So there's a couple of terms here, primary and secondary. So we've got primary, which is the voltage is applied to. So primary, the transformer, where the connections, let's say the winding connected to the supply. It could either be, so each of these is a primary winding. I don't see a secondary winding. I don't even see a winding. Just a piece of wire. Each of these can step up or step down voltages. So the primary could be the low voltage side or it could be the high voltage side. You could be stepping it down. Like here's a control transformer. This one is 600 volts, to a selection of 120 or 240. So it's stepping down the voltage. So the primary in this case, if I connected 600 volts to the 600 volt winding, that would be the primary. If I connected 120 to the 120 volt winding, that would be the primary. So I get to choose where I apply the source. So that's the primary, where the source is connected to, where the supply is connected to. And the secondary, winding connected to the load. Pretty much in a nutshell. It's not high or low voltage, could be either. Because there's a lot of confusion as to, when we get into the book, I'm going to look at a diagram and make you change it.
For the transformers, can you always hook them up either way? If you buy a 600 to 240 volt,
Yeah.
is it always interchangeable, which is supply, which
Yeah.
is load?
Yeah, it's usually, yeah, it is. It is. It's just what's conventionally done is usually stepped down, right? But say I had 480 volts in a building, and like in Langley, and you wanted a 575 volt motor hooked up. Well, if you use 480 on a 575 volt motor, which is basically 600 volts, it would run too much current. It would try to labor in its spinning to try, and it would suck more current from the source. So you'd want to step it up. So you could use a 480 to 600 transformer, but that transformer could also be used in a different situation, 600, and you want to put it down to 480 to connect that 480 volt equipment. So sometimes you're hooking it up at the equipment or on the electrical room before going over to the equipment. Yeah, good question though. Yeah. So I wanted to just bring that out because, well, we'll get to this in a second. If you put these in two beside each other, now you have induced voltage. So which side has the induced voltage? Right side. Okay, so this would be the primary source, the primary conductor, because I don't see a coil here, so I'm going to call it a conductor. And this would be the secondary conductor. It's not connected to anything. It's only close in proximity. So if that was the case, and in this case it doesn't look like I have an iron core to share between the two, so it looks like it's air. Wouldn't be a very effective transformer, but it is a transformer. You're transferring electrical energy from the source circuit to a remote load circuit, or a separated, isolated, you could say, it's isolated, it's not connected to it, load circuit. So using the left-hand rule then, okay, I've got current flowing through this guy. Okay, that means that this would now have a magnetic field around it, but when the flux is expanding, okay, and I think it's probably worthy of just drawing this out. If you guys maybe take in your book or redraw it or whatever, let's draw this. That's the source. And then we got this guy right next to it. Do I have to connect a load for it to induce voltage into this second wire?
No, there'll still be there'll still be voltage across the.
Yeah, so if I had an open switch, there would be no current, but there would be voltage across from one side of this wire to the other that's being induced. Okay, but if I close the switch, then I'll have, because I have voltage, there will be a flow of current. So it's like a generator. It's using another form of energy, which in this case is actually electrical energy instead of mechanical energy, like a generator. But if you put this electrical energy, you're taking one form into another form. It happens to be the same form, but it's transferring that energy from one circuit to another circuit with no electrical connection. Okay, so looking at the field, then, so if this side is negative right now and this is positive, And we've got a flow of electrons going this way instantaneously now, because that's how they've drawn this. And then I've got the field produced. Well, we know that if something is in close proximity, those flux lines will envelop the whole situation instead of just the one wire. You won't just have it around this one, it'll be around the whole thing. So when this is expanding, that's a bad diagram. Okay, there we go, right? Something like that. So if we're expanding outwards, this current is flowing this way. This is negative. This is positive. Does everyone agree so far? Just in case I make a mistake, because yeah, it comes up. Okay. If I say, okay, that's expanding now, what's the left-hand rule you use for generating a voltage? This guy, right? And the result is the middle finger, right? What's that? Fleming's left-hand rule. Awesome. Okay, so that means the flux is set up. So if I take this conductor and I say, okay, I'm going to take this half of the conductor and I'm going to say right now, the flux is expanding outwards across that conductor, right? So it's like it's expanding outwards. So if that's going that way, then which way is the conductor, like the conductor's moving? It's like the conductor is going the opposite way. But is the conductor moving? No. Just shake your head about that. Okay. So yeah, because the transformer is, if this is a transformer, which it is, it's not moving. It just sits there and hums. I don't know what it's humming. So, and it's humming because it's actually causing a motor effect on the core, which causes it to vibrate back and forth. And in DC, you won't get that. Okay, so the conductor's going this way. Which way is the field on that side of the conductor? Well, maybe we should use, let's use the outer side. Maybe, I'm going to just change the side. Same thing. So let's say it's going that way. Would that be the same? If this is expanding, that means that we're going to look at this half. Which way is the field going at this side of the conductor? That way? So if it's going, if the field being set up by the original primary conductor is going this way, then that means that it's coming around the other way, around this conductor. So then the field's direction, this is the flux motion, and this one, 3D-ish, is coming at you. Let's say it's coming at you, and that's the flux's direction, that direction, at you, right? So, that's the direction of the flux, that's the forefinger. If the motion of the conductor is opposite to the flux's motion when it's expanding, because I said it was expanding, then the conductor motion is going this way. So I should induce, would that work? Maybe.
What about the other rule?
Yeah, I guess so. Is that the induced voltage? Did I screw it up? What's wrong?
Just the other left-hand rule where you have the flux lines and then the current going that way.
Mm-hmm.
Why would that change?
This one is causing the flux lines. If this switch is open, let me just do this way. There, open circuit, voltmeter. I'm gonna do it that way. When the flux is expanding, it's cutting across, and it's like if these two insulations on the pieces of wire are touching. I can't draw that, I drew them like this. But let's say they're like right tight together. So that means that the flux is happening around one wire and the other wire at the same time. So if this is expanding out in this direction, the conductor motion is that way. The field is coming around, and that's why I did this half. That's why I did it on that half, because I could tell you where the field was.
Is it because on the left half, the primary, the current is causing the field? On the secondary, the field is causing the current?
Yes. Yes, it is that actually. Because this is a counter EMF. So this is the induced, let's call this the induced secondary voltage. So how it works is you've got this primary voltage, we'll call this applied voltage. There's my applied voltage in that direction. You have your secondary induced voltage, which is your generated voltage, in the opposite direction. So what happens there, what would happen in this first conductor? What would that be if I did not even have this covered up? What if I didn't even have this circuit in there at all? What would be that voltage, that generated voltage I just drew there? The generated one. If I had only one wire to look at, would I have anything happening in that first wire? You sure? Flux is expanding across the conductor. It induces a, even though it's very small in this case, because it's not a coil, it's a counter EMF, right? So the counter EMF in the first wire, so this voltage here, this induced secondary voltage, is in phase with the counter EMF in the primary. It's in phase with the counter EMF in the primary. And so that counter EMF is probably pretty small. Let's call it there. Because it's not it doesn't have much inductance. When we get to a coil, it has tons of inductance. So inductive reactance is the main thing. And what causes that reactance? Changing voltage, or changing current rather, expanding, collapsing flux. Expanding, collapsing in one direction, expanding, collapsing in the other direction, constantly like this. So that would be the limiting factor in the main circuit would be because that counter EMF caused less net voltage across it. You know, that's the principle behind it, which we've already learned. So that counter EMF is in phase, and I'll do the induced one here in blue. See, in phase with that guy. So you could say that the generated voltage and counter EMF, you could draw the counter EMF over here in the primary, or they call it negative E generated in the book. The book, they'll call it negative E generated. So it just means that it's countering, and you already know this, when you have negative, it's an opposing voltage rather than an aiding voltage. Okay, any questions so far? Is this fairly clear, or like, if I totally lost you? Okay, so the generated voltage in the secondary, if this is the primary, and this other one is the secondary, that's what's going on from primary to secondary. This circuit, although the values of the vectors are a little large, that's the principle behind it. There's 180 degrees opposed, is the counter EMF. These two, from primary to secondary, are in phase with each other. because when you're generating one in the primary, you're also generating the same one in the secondary. If I drew this arrow a little shorter, is that better? Maybe. Maybe that makes more sense. So whatever you induce in the primary, you'll also induce in the secondary. Okay. There's a method to this madness. All right, let's go to picture. You guys like pictures? Yeah, there you go. Here's a coil and an iron core. That's primary and secondary. I'm trying to figure out which way the coil goes here. So this one goes around this way, and this one comes around this way. Is there any electrical connection between the two?
Well, we can't see what's behind the core.
Yeah.
Yeah, so the flux is expanding, and it's causing an induced voltage, and this is the polarity they've given. So I'm not even going to analyze the polarity on this particular diagram, so just because sometimes they screw up. But just the idea that you're transferring electrical energy through magnetism, through a changing flux, and that's it. If you have motion, if you have field, and you've got those two, the third ingredient is an induced voltage. Right? Fleming's left-hand rule. It's a generator, only it's not a generator. It's a transfer device. I don't know how far. Yeah. Okay, we'll get into that later. But transformers transfer AC electrical energy. DC. Is there any limiting factor on a DC coil?
The resistance in the wire?
Yeah, very small though, right? Could be 10 ohms, could be something like that. Very, very small. So you gotta be, or 1 ohm, right? Could be even smaller, 2 ohms. But if there's AC, and you know you've done this in the lab, when you try AC on a coil, now the current just drops right down, right? Why? Inductive reactance. Why is it reacting? It's an opposing voltage, a counter EMF. Every time the flux is changing, you have an opposing voltage being generated inside that coil. So it's the same thing. Or we go back to this thing. So in this case, it's a coil and an iron core. Better than air, better than a straight piece of wire. They say that they're very efficient. Primary winding is the source, and the primary winding receives the energy from the source, and the secondary winding is connected to the load. It delivers the energy to that load. So one's receiving the energy from the source, changing it to magnetism. The cutting of flux cuts the other conductor, takes that voltage, if it's connected to a circuit, and delivers that energy to the load. So energy in, energy out. Right? That's pretty much it. How far are we here? Pretty fast one. Here we go. Here's a basic transformer. How far did I get to? 11? Are you on the page? Okay. Primary winding, secondary winding. In this case, it's true. Primary winding, secondary winding. These have the same number of turns. So how many turns do you count on that primary winding? 3? Okay. How many turns do you count on the secondary winding? Because I already told you they have the same. 3. Okay. I'm not trying to make you think too much. Okay, so voltage, in this case, the primary voltage will equal the secondary voltage. If the turns are the same flux from the primary transfers to the secondary across any active portion of conductor, and you're going to get the same voltage out. So this would be like an isolation transformer. So a lot of times you'll do this in an office, say a warehouse. You'll have a transformer just before it goes into the warehouse offices for computer loads and various things. And you'll have a 1-to-1 ratio. You know, 240 or 208 in and 208 out. That's pretty much it. And you think, well, why did they do that? Because they're isolating it electrically from high voltage spikes and other things that happen on the supply side. or they're protecting hydro from all those computer loads, because they have like fast switching going on, and that causes harmonics and different things to hydro. So hydro doesn't like that. So it's an isolation. It'll isolate it electrically, but still transfer the energy to it. So that's one purpose of a transformer. So EP and ES. So this is a really easy one. I'm going to teach you a formula. Probably already read. How many read ahead? Learning task 1 at least. Okay? Okay. So EP to ES. So if I had 120 volts on my supply, if I had 120 volts on my supply in that one, and I'm going to draw it like this. And then I have a load. If it's the same number of turns, I would have 120 volts here. So I have 120 volts across this winding, 120 volts across the other winding. So this is E primary over E secondary equals, to move it over a bit, one to one ratio. Guys, I'm going to go through this, and I'll show you these formulas, and there was one level 2 class I went through, and at the end of the day, one guy says, is this like super extra easy or something, or am I missing something? I said, no, you're not missing something. You've just gone from these really difficult topics, and now you're going to something basic again, right? Because you're just being introduced to this. So it's actually pretty basic. There's a couple of rules you got to know about transformers, and if you apply those rules, it works every time. So 1-to-1 ratio is primary to secondary, and that's usually how you refer to it. So 1-to-1, or 1-to-1, if you know that which one is referred to as the first number, would be the top, be 1-to-1. So just to recall ratio notations. The ratio of turns from the primary to secondary, well, if I had 3 turns, NP equals 3 turns, and secondary equals 3 turns. Now I'm going to use the turns, so I actually physically counted the turns or something, right? 10,433 turns, right? Who knows, right? So I actually counted the turns, which you don't normally do. Well, that would mean that the same ratio is true. 3 turns over 3 turns is a 1-to-1 turns ratio. What's this one? Voltage ratio. They're always the same. So voltage ratio and a turns ratio are the same. So if it's 2-to-1 on the voltage, you know that the turns also have to be 2-to-1. Or let's say you've made your own transformer and you've done 100 turns and 50 turns. It's 2-to-1. So I'm going to step down the voltage to half the voltage I had before. Right? It's really basic. So it's really all to do with the turns ratio, how it's constructed. So then if this is equal, then it can be said that EP over ES equals NP over NS. And you can figure out almost anything from that formula right there. The 2 ratios are equal. I'll get to some examples in a second. Here we go. So here they give you one example. Let's try this example. Oh, I gave that example. That's funny why I came up with that in my head. 100 turns in the primary and 50 turns in the secondary means what is the secondary voltage?
60.
You can do that in your head, but how do you do that mathematically? Well, I'm going to say, what do I not know? I do not know the secondary voltage. So let's take the secondary voltage equals, and you can kind of do it this way now. You can go NS over NP times EP. Right? Or this one you could do here. But if you're careful and always follow the formula, you won't screw it up. Maybe you might screw it up if you do it in your head sometimes. Like have it in reverse. So I'm going to say, okay, secondary turns. In this case, we're 50. 100, so that's half. There it is. So make sure you get it the right way. Half of 120 volts. I think that's 60 volts. Excellent. What do you think? It's the same.
No way.
What did they do in the book?
Current is the same.
Okay, it's how they drew it. Their NS over NP is over here. That's all. Same. I like to think of it as it's the secondary turns over the primary turns times the primary voltage. It's really it's like how many ever left. What if I had 200 turns on the secondary?
Change it to 50 over 200 something.
Would you just
No.
step up to
50
240?
over 200.
Okay, so let's
240.
240.
I know that you laid, or you laid, you don't actually pull
Secondary coil? Yeah.
200 turns. What if I have 200 turns here? What's my, this is E primary. What's the secondary voltage?
240.
You can do it in your head, right? But how did that work? Well, you took this and you said, okay, NP, or sorry, EP equals NP over NS. You think I'm wasting time by doing it the long way?
No, well, you probably.
I feel like I am, but I always try to do it every time, just so that I don't screw it up. 200,
The same voltage. with twice
Or,
the
sorry.
voltage, you just do voltage times 2.
what am I doing? After secondary,
120 would have.
it's the same formula as that one.
2.
My bad. See, I almost screwed up because I didn't.
Makes sense.
That's better, because we're still trying to get the secondary voltage. I did it as if I wanted to get the primary voltage. What if I had the secondary but not the primary? You can solve for any missing component. And so I'm going to say, okay, now it's 200 turns over 100 turns times 120 volts gives me 240 volts. Good. So in this case, it wasn't a step down, it was a step up. So knowing your theory that you've learned of generating a voltage across the active length of a conductor. So active length, here's a wire talk. There's no wire in this place anymore. Active length of conductors, pretend it's a wire. So whatever part is active is the part that generates voltage across that piece of wire. When it's in a coil and it's wrapped around a core, every part of that wire is the active length. Every single part. And around that same core is also another set of wires. So you could have a core like that, something like that. That could be the primary, and that could be the secondary. It doesn't matter where it's connected in that core. It could be on the, they show it on the other side. It's usually wrapped around the same section because it's inducing a voltage into that secondary conductor, which is in the shape of a coil, and the leads are brought out wherever, just so that you can use that voltage for your load. right? So they didn't have the primary and secondary. That's a 1-to-1 ratio there because I got 2 turns on each one, right?
If they're on the same side, is there ever any interference?
The interference, well, yes, I shouldn't say no, yes, but it doesn't matter where they are. These wires could be anywhere, and it's the core that it's the flux that causes everything, right? So if that flux is contained in the core, it doesn't matter where that secondary is brought
The
out.
flux doesn't affect the wires because it's sucked to the core.
It's not the wire's proximity, it's the core, it's everything is how close it is tightly knit to that core. The core is the main part of the transformer that does the work, that contains the magnetic field. So yeah, so that's why I'm saying it doesn't matter where I put it on the core. And it will have interference when there's a load attached to it. But when there's no load attached to it, it'll have no interference. So in this case, if there's a load, yeah, it's going to have some interference. And we'll get to that in learning tasks like 5 or 6 or something, I think, somewhere in there. Okay, so far you've learned that you can induce voltage into a second conductor through either a close distance or through an iron core, and it's the changing flux that does it. The generated voltage is the secondary voltage, which is 180 degrees out of phase with the primary voltage. How would that look sinusoidally? Well,
Check the sinuses.
if my primary is doing this, the secondary is doing this. Right?
Yes. Pretty close.
Is it? Yeah, that's bad. You get the picture. What about current? Okay, let's make this the 200 turns. I'm going to change the question to this one. I said that it's 240 volts. So this situation is gone. We got 240 volts on the secondary. So what should I do then? I should write down my answer, 240 volts here. What's my ratio? This transformer. Okay, but is it? 1 to 2. 1 to 2. So if you put the ratio in the core, just draw it right over top of the core section, then you can see what it's doing. It's like input output. Input, 120 output. If I do that, let's say I had a 10 ohm load. What kind of current would that be in the secondary? So you can't determine the primary current, you have to determine the current draw from the load, right? So whatever's on the secondary is going to determine the draw of current in the circuit. So what would that be? 24 amps? Okay. Secondary, 24 amps. Okay. Well, if you use the VA principle, and you say, okay, well, how many volt amps is that? Can you do that in your head? Is that
5,760.
what was it?
5,760.
Oh, yeah, it's double what I said. Okay, 5,760 VA. Okay? One of the main things about transformers is another formula, VA in equals VA out. I'm giving you lots of options here on how to solve these. So far you've learned the turns ratio and the voltage ratio are the same. You've learned that, because I just told you this, VA in equals VA out always. There are losses in the transformer, yes, but this is not watts. This is VA. And we'll get to flux linkages and that kind of stuff later. But VA in equals VA out ideally. Okay, let's say in an ideal transformer, a perfect transformer. So what is the VA in? If this is the VA out, VA VA in equals 5760 VA. So what is the current in the primary? 5760, going too fast?
No.
Divided by 120 volts, instead of dividing by 240, we're dividing by 120, higher current. Okay, so 48 amps, yes. So remember I said that the same energy delivered from the supply when they had 240 volts and 100 amps in your house, and the supply might be 24,000, it's actually 25, but say it was 24,000, it'd be 1 amp. Well, the opposite is true, that if I had a 120 volt circuit at 48 amps coming in, or let's say I had a 240 volt circuit with 24 out, a 120 volt supply to that through a transformer would actually have to draw more current to achieve the same VA. Double the current. Yeah.
Is that an isolating transformer?
Yes.
I'm just wondering, because the 10 ohms from the load is affecting the current from the supply,
Has to.
but it's isolated. How
Yes.
would it affect it?
Well, I don't think okay, I put it to this way, I don't think a transformer would be very useful if it didn't actually draw current from the secondary. So then we have voltage and we say, yeah, but we can't use it. Right? Your house, 24,000 volts, they've stepped it down to 240, and you start plugging things in, yeah, this doesn't work because it's through a transformer. No, and we'll get to why that works, okay? But the energy energy is delivered somewhere, energy has to be supplied. So the VA out has to come from somewhere and the VA in, right? Think of it as watts, you know, the energy out is the energy in, and so it'd have to be 48. Yeah.
The VA in equals the VA out, where because there's losses in this, right?
Yes, but we're not getting into the watts of this.
Oh, so we're okay.
Yeah, but I'll get into that, we'll get into that later, but you're thinking in the right direction.
Okay.
You are, and I called this an ideal transformer.
Right, yeah,
So-
okay, yeah.
And it generally will be, I mean, the VA in, this is a 500 VA transformer. This one's 500 VA. We can do a calculation based on this one. I'll actually use all of these as examples coming up. Okay, so we've got here current. So we can add one more formula to this. It looks like when the voltage is low, the current is high. And when the voltage is high, the current is low. So the current is inversely proportional to the turns ratio. When there are lots of turns, small current. The wire can be smaller on that coil side. So if this has 200 turns, it's not going to draw as much current through those windings, so the windings can be half the gauge, you could say. I don't know if it is half, but it'll be smaller. So you could say that another part of this formula is the oddball IS over IP.
You always draw it like that? Your current secondary is always above your current primary?
If you've drawn these other ones this way.
Correct, yeah.
Yeah, yes. So it's the only one that's inversely proportional to the ratio. So this is a 1 to 2 ratio, 1 to 2, 1 to 2, 2 to 1. Right? Or sorry, 1 to 2. But the current on the secondary is half. So it is 1 to 2. In every one of these cases, it equals 1 over 2. Right?
1 to 2, 1 to
Does that
2.
make
Not
sense?
go 1 over 2, 1 over 2, and then 2 over 1.
Well, you can't go 2 over 1 because I put secondary up here,
Voltage.
primary down there.
Current.
Yeah.
Yeah, so it's 1 over 2, 1 over 2, 1 over 2.
Okay. So they have to be the same, but they're still inverse.
Yeah, the current ratio is 2 to 1, but we don't use that. We use the voltage and turns ratio as your main ratio, whatever the voltage is doing. It's based on the number of turns. So think of it that way, turns, turns, turns. Do you ever see something? Turn, turn, turn.
Last one's
Birds.
because the current
Birds.
is inversely
Want to
proportional.
get the birds? You can Google birds later. Good song. Okay, There you go. So they give you an example. The secondary current was 50 turns, so they said this was 60 volts. So you could figure that out. If that's 60, how many amps is that?
6.
6? Okay. So let's try their way. Instead of doing VAs, you could do this way. You could say IS equals 6 amps. So then you use the turns ratio and this one here. So you could say NP over NS equals IS over IP. So IP would be NS over NP times IS. Because you know it was 6 amps. So 50 turns over 100 turns times 6 amps. So it's 3. It's 3. So the primary, because it's a higher voltage, actually drew half the current. And the principle behind this, which is probably why they don't introduce it right this second like I did, is VA in equals VA out. For that current to be true, VA in has to equal VA out. It's almost like I'm just showing you part of it. Oh, there it is right there. VA equals VA. Okay, so neglecting the very small losses, it says, due to heat and vibration, power is always equal to power out. So that's why we don't call it power, we call it VA. Because there are losses in there in watts. So you might not have you might have a purely resistive load, but then again you might have a heavily inductive load. Right? Who knows? But in every case, VA in equals VA out. You don't have to care about the load. Just that's how it works. Symbols, you know this. That's an iron core, air core. Classification of transformers. Okay, transformers, has anyone involved in the field on a regular basis or just once in a while? A little bit, transformers? Yeah? 3 guys? Okay, that's good. You may have been involved in other people doing it, you've seen them do it. If you ever get a chance, and I'll show you the one in our, we've got a couple in our shop, read the nameplate on them. Because they don't list the current of the transformer, they always rate them in kVA and voltage. And you have to determine what that current is on your own. Right? So it depends on the connection. So transformers are either they're forced air, forced oil, natural, or they're just plain oil, in oil. You have to cool the windings. Think about it. If you have 48 amps on this transformer here, it's going to get pretty hot, right? Because it has a certain resistance in the wire, in the coil, that would be I squared of that R in that wire, cause heat. Okay, so that's the main issue. We call those copper losses. So you got to cool it so they don't melt. You don't melt the windings. But a lot of times it's just air. So a dry type transformer, which is basically a winding. Do I have maybe a picture of a dry type transformer? Dry type. Okay, I like it. Oh, that's not very big. Maybe too small. Too small. Look at that one. These are 3-phase transformers, but just disregard all the extra windings. There's 3 windings instead of 1 on each leg. Oh man.
John Cuddy's
Hey. Oh, it's a horrible picture. But anyway, you get the idea. You get the idea. What's the cooling method there?
Air.
Air. Yeah. What about the ones out on the pole?
Aren't the transformers up there in water?
Water.
Aren't they all submerged? Oh, wait, no, they're submerged to make sure they're watertight.
Okay.
I saw that on How It's Made, this is.
Yeah, I mean, they get wet. Level 3, it expands on this. It's like, hey, remember what you learned in level 2? Here's new stuff. That's how level 3 works. So just always try to keep your books. That's how you listen.
Big little teeny.
Number of phases. What's polyphase?
More than
one?
Four.
Yeah, more than one.
More
So
than-
there's 2 or 3 phases or whatever. You could have 6 phase, 9 phase, 12 phase, but we don't use it. We only use 3 phase. Be too many wires. Type of service, types of transformers we will get into. There's differences between power transformers, distribution transformers, instrument transformers, and control transformers, like this one. Control transformers. Type of windings, whether they're isolated or something called auto transformer. An auto doesn't mean a car. It means, it's almost like the word auto is a prefix in English to mean like autonomous, if you want to think of, what other things are there?
Automatic?
Automatic, yeah, something that works all by itself. It's a single thing. So it'd be a single winding, no secondary winding. And we'll get into how that works coming up. Next one. Trying. The scroll is. So we learned this. Assuming 100% efficiency, VA in equals VA out. So the turns ratio equals the voltage ratio equals the inverse of the current ratio. Right? NP over NS equals EP over ES, but IS over IV. All those are equal. If that is true, if you say that, and we're getting into this part now, there's a third thing, which is the same. So we've learned this. Another thing that's true, if you take this part of the formula, right? You could transpose these guys and still have it equal, right? You could say that EP over NP equals ES over NS. Anyone disagree with that? Could I not say that that's also, because I've just moved them around, and I still have the equal sign, so it's got to be true. Okay. That is the voltage per turn. This is called volts per turn. So the volts per turn on the primary equals the volts per turn on the secondary. Well, is that true? Let's try this example we just did. Another color. So what is the volts per turn on the primary? Equals EP over NP. What's that? 120 volts over. How many volts per turn? 1.2. Every coil of wire has 1.2 volts induced across it on the secondary. 1.1 primary, it was supplied with 1.2 volts. So the same induced voltage, but 180 degrees out of phase on the secondary is 1.2 volts. Also is true that if I take this, because we've already solved it, I'd say, okay, the volts per turn on the secondary. Let's try that one. ES over NS. So what's secondary voltage, guys? 240. Okay. And it was 200 turns. 1.2 volts per turn. So, knowing that, that's really important, so that the volts per turn on the primary equals the volts per turn on the secondary. So that's what that is. Volts per turn on the primary equals the volts per turn on the secondary. And you can say, okay, well, if I had if I have this, what if I have 300 turns here? 300 turns times 1.2 volts per turn,
360.
360. Isn't that just 3 times the voltage?
Correct.
Yeah, so there's different ways of skinning this cat. You could say, I'm going to use volts per turn. Or I'm going to use VA in equals VA out. I'm going to use turns ratio equals voltage ratio. So it's all, you can check actually different things to make sure you have it right. So we got this one. Then we add current. Then we set that. And now volts per turn. So what is equal on both sides of the transformer so far?
The ratio of,
VA in, VA out.
Each turn is worth the exact same. You just have to.
Okay, volts per turn. That's one answer. Volts per turn is the same on each side. Doesn't matter how many turns, but the per turn is the same, right? Each turn. Okay? What else is true? Loading of loading.
Your voltages.
VA in equals VA out. Exactly. So those two things are equal. So this one is dealing with both sides, right? So this can't be the formula. So these two are the things that are equal from one side compared to the other side. VAs are the same, and the volts per turns are the same. All right, so let's see what they do here. What are the volts? Don't look at your answer. Let's try to do this one at the bottom here without looking at the answer. Is that big enough? No, that's not. There. What are the volts per turn of a transformer with a voltage rating of 480 volts to 120 volts? What does that mean when it goes 480V dash 120V?
What do you want? Is 480?
Yeah.
It's just saying it's like 4 to 1.
So what they're saying is that's from one side to the other, and what they're saying is the primary is 480 and the secondary is 120.
So is it 420?
So I would draw it like this. Always draw it. Okay. So that's my source. My supply is going to be here. Primary. This would be secondary. So far, so good? Okay. What are the volts per turn if the, high voltage winding contains 200 turns? So which one is that?
The source winding.
In this case, it's the primary. So the high voltage winding, 200 turns. Okay, good. So what's the volts per turn then of this transformer? 2.4. So volts per turn equals, in this case, EP over NP. Do I have to worry about doing the secondary? It's the same. It has to be the same. So this is what is supplied by the source to say that that is in that section of wire, it's 2.4 volts from here to here. And in the secondary, it's also 2.4. And it just depends how many of those you have to say what voltage it is at. Okay. Nice. How many turns would there be in the low voltage winding of question 1? So how many turns? How do I deal with that? So I want to know NS, right? Well, if they're the same, we can say that if this is true, then we could say that ES over NS is the volts per turn
So one's going to be divided by 2.
equals 2.4 volts per turn, right? So there's your statement. What is the secondary voltage? 120, so then NS equals
Yes.
ES
Divided by-
over 2.4 volts per turn, 120 over 2.4 volts per turn, volts cancel, and I'm left with turns.
50.
Okay. There you go. So just another way to do it. Hey, they did the same as me. If a transformer has 300 turns on the low winding and a voltage ratio of 208 to 240. Okay, so 208 to 240. You guys want to try this one? Without looking?
No hands.
No hands? Yeah. Look, Mom.
No hands, it does take that car.
So I would draw it. And fill in the information that you do know. So where does the 208 go?
On the east side left. I guess it doesn't matter.
This one doesn't really matter which way you connect it because we haven't connected to a power source. They're just saying how many turns are required. But when they do draw it this way, 208 to 240, that usually means to apply the 208 source. A lot of times you want to bump the voltage up a little bit.
Theoretically, if you wanted to, you not move your like source voltage to the right, you move 208 to the right, like just like swap the whole equation and it'd still be okay.
Yep. So what's the volts per turn? Did they use volts per turn? Good. Glad you don't know. No one looked.
Lock it inside of it.
I want to see who looked. I'm going to use volts per turn. So
The honor system.
208 volts over 300 turns. Is that right?
Yeah.
What's that come out to? I don't know. Roughly 2/3, right? 0.6 something. 333. Okay. You don't have to do it this way. They're just doing it this way to show you. You could store that in your memory and say, okay, well then 240 volts divided by that should be my turns, right?
That's right, yeah.
Yeah, so I'm going to say, okay, I'm going to say the secondary turns is going to be the 240 volts divided by 0.6933 repeating volts per turn. And I end up with turns using my physics background. You take, okay, it's bigger than 240. It's going to be
346.
346 exactly. Turns. Let's see what they got.
Non-sig figs.
Okay, why did they do it this way?
Because it's the easier way.
Because it's easier. Sometimes the volts per turn method is not as easy. So when I asked you, did they use volts per turn, no one could tell me, which is good. But we got the same answer doing it this way. Or you could plug it in, I've got voltage on both sides, and I've got turns on one side. I can get the remaining turns just by using EP over ES equals NP over NS. So go to that one when it's easier. If the numbers don't work out and you have to like store this number in your memory, right? Why go through all that? Why don't you just do it this way and say 300 divided by 208 times 240? Got it. Boom, done. Okay.
Yeah.
A step down transformer. So where's the high voltage then?
On the primary.
Primary, okay. Has a primary current of 10 amps flowing. What is the impedance of the load connected to the secondary? Ooh. Impedance. So what do I draw?
Stop.
Enough? Okay. There's less turns on the secondary, right? Probably roughly a third of the turns, well, not quite, maybe more than a third of the turns, right? 40%. Something like that. So this is the supply, right? How would you like this one? This transformer, 600 to 240. Then they say, I've got how many amps did I measure in the primary? Okay. How do I get the impedance of the load in the secondary? Well, first of all, we got a connection. Right? I'm going to use VA in equals VA out. Probably easier. So what's the VA in?
6,000.
I have to show my work. Do you guys know how to get VA? Right? Okay, 600 times 10? 6,000? Okay, equals VA out.
It's also 6,000.
So it's the same, 6,000 VA. So the current in the secondary, if I had an ammeter there, equals 6,000 VA divided by 240 volts. Easiest way, actually. I prefer that way. So we go to way, the VA way.
That's 6.
So what's the current? 25 amps. Okay, 25 amps. So 10 amps, is that, you gotta ask yourself if it makes sense that it's bigger.
Yeah. And your proportion is 2.5.
2.5 to 1.
Yeah,
Okay.
so theoretically, could you not just go 2.5 times 10?
Yes.
And then go current of your ES divided by your...
Yeah, but you did it this way. So
Okay.
whichever way we want to do, yes, we can do it that way too. Okay, 25 amps. So the Z, how do I get Z? I don't know. So, oh, there you go. So it's a two-step question. Get the amps, then get the ohms. How many ohms is that? Awesome. So how did they do it? They did it this way. Same answer. So do you like that? Now you got a few options?
Yeah.
How hard is that?
So you...
7 out of 10 easy.
telling us they're gonna change the load. They're changing the load now to 5 ohms. So they're gonna say, I want 5 ohms changed to that, okay? So what current would be in the primary? Well, I need to know the secondary current before I get the primary current. So 240 divided by 5 ohms,
Math question.
48?
Yeah.
Okay. So now it's not that, it becomes, with the 5 ohms, becomes 48 amps. Does that make sense?
Yeah.
Okay? So what did they ask? What current flows in the primary? Of course they did. Or you could do it this way now. You could say, well, VA out is 48 times 240, and then go and take that VA divided by 600. Or you could do Clay's way, 2.5 to 1. You could basically say it's divide that 48 by 2.5, and you'll get that new current. Right? So what is it? 19? Yeah.
19.2.
19.2 amps. Okay. So now ask yourself, does it make sense that it went up? Because it's less ohms. So yeah, that's, so the secondary affects the primary. There you go. Okay, so go through some of these on your own there, and I'm going to go to Learning Task 3 just to get this finished. These are pretty basic. It's just introducing these couple different principles now. I want you to change something in your book on page, very first page of Learning Task 3, page 23. Change this to, instead of primary, change that word there to high voltage, and change the other one to low voltage. It corresponds with the description. What they say is not untrue. What they say is true. It is a primary and it is a secondary. But the 3 major parts are going to be not the primary and secondary. Those aren't parts. Those are applications. Those are like, I'm putting voltage across, pick a side, and I'm taking voltage off, pick the other side. But it doesn't have a correlation between high and low. So I think for the parts, you want to say one is going to be a high voltage winding and the other one's going to be a low voltage winding. Sometimes they're the same voltage. But let's just call it the 3 major parts. And if you get this wrong, I'm going to kick you, because I told you to change it.
Where?
High voltage. Pick one. I don't care where the high voltage is, as long as one is the high voltage and one is the low voltage, instead of primary and secondary. Okay?
High voltage.
Because then they go and they talk about it here. Okay? This is what you want to remember. That one is many turns, relatively thin wire. What did I do, Rancho, here, when I drew this 600 volt side versus the 240 volt side? Just for picture purposes.
No, that only turns it on.
Like a hell of a lot of turns I drew there, and Eric said for me to stop.
You trying to tell me Bob's not an artist? Dude, is that what you're saying?
For your own good.
That's also
Eric's a protection.
So anyway, high voltage is many turns, and the wire can be thinner because the current is
Less.
smaller. Yeah. And the low voltage side has fewer turns of thicker insulated wire. Because volts per turn is less, or volts per turn is the same, but number of turns would be less, so the output voltage would be less. But the current from a low voltage side is higher for the same power on each side. Core flux, so the core has high permeability, low retentivity, and high electrical resistance. How did they change the electrical resistance of this transformer core?
By, using
Lamination.
the layer thingy?
Laminations.
Laminations,
This is
that's.
gonna come back to you every single time, so like, everything is made in laminations in the core, so that it limits eddy currents. Eddy currents.
Sensitivity is like, it's holding the charge out.
You don't want it to hold magnetism because then it has less permeability to deal with remaining, because part of it is already magnetized. So that would be bad. So high permeability, low retentivity, and high electrical resistance. Why is it silicone steel? What does that help?
Protection.
Gives the steel
Compromise
higher
must be
resistance
the
against any current.
Silicon steel.
It's actually, it's funny, it says it's higher resistance, which is true, but it had another feature we learned way back about cores of coils, inductors. Yeah? For what purpose though? It mentions it here. What's another main reason? You guys learned it before.
Like laminations, is that what you?
That's more to do with eddy currents. The silicone helps that, but it's not the total hysteresis. Yeah, hysteresis. So that it reduces the hysteresis opposition in the circuit.
I don't think right there.
Oh, no.
Anyway, it's okay.
Come on, dude.
Efficiency. Let's finish up here. Power out over power in. Does that look like a new formula or an old formula?
No, I seen that one.
Yeah, you
I think I saw it sometime in May.
saw
Okay.
it before.
First year?
We got a funny little end there.
You knew what I was.
Why does it say power out plus losses?
Because it's,
Field transformer is perfect.
including the loss in,
Kilometers.
Yes.
Exactly.
So
Very,
I have
very strong.
power in, and then I have power out.
Oh, you
I
lost
lost some.
it. You lost it.
Went into some other form, right? So it's the initial with losses that is the total power in, right? Hasn't been lost yet. Is that a good example? Should we do that again? Power in. Power out.
It's gone, just like my dad.
Okay. You know, the fist pump thing, right? The electrical code. I know you guys want to go because it's been a long day, but KVA, here's some things the code says it has to have. You have to list the KVA, so this one says 500 VA. So it's this is half a KVA. Right? Okay. High voltage winding, low voltage winding. Okay. 600 volts, 240 volts. Excellent. Number of phases. Doesn't say, but the drawing shows me it's single phase. Okay?
Do you have to know like every single one of them?
Yeah.
Frequency, would that be important?
Yeah, that would probably be important.
So inductive reactance on the primary would be affected by the frequency, right? So 60 hertz. Now this one says 60 hertz. Can't use it on 50. The voltages would be out of whack. Polarity. We're going to talk about polarity just very briefly. And then we'll go on. Polarity.
John is good. He misses on the jokes. You feel like you
Sure, so that thing, yeah, you got triggered once you tried to break it, and then certain values like what Sag Jason's not
He does. H1. The other one's got to be Kyle.
Oh, H2.
Yeah. Okay. So I have two transformers. You always always do that.
No pictures.
That's what we know.
Each one on the left.
Let's say all the markings have been rubbed off. Okay, so that means at the low voltage side,
It's not seeing.
I'm gonna say, okay, when the terminals, when the wires are brought out, either one over here and two over here, one over here and two over here, then it's going to be either additive or subtractive. And we'll get into why later and go into it later, but I need to at least to be able to identify which one is additive and which one is subtractive.
I'll tell you.
This one here, and this one here. Which one is which? Which one's additive and which one's subtractive?
The one on the left is additive.
Yes.
No?
It's got nothing to do with the way they're wound, because you don't want to screw up the loading of a transformer by winding it the opposite way. They always have to wind it the same way. It's how the leads are brought out. And I used to think that it was wound differently, and I got literature that shows that, but I figured out finally that no, it's just the way the wires are brought out for connection purposes. That's all it is, okay? And we'll get into why this is important. And this one then obviously would be subtractive. Okay, so going into this, just finish it off. The other one is percent impedance. We're going to talk about that in our whole transformer unit eventually. Temperature rise, coil capacity. Make sure that you put the gauge on if you have the gauges when you're installing the transformer. We forgot to thread on the gauge, and then now it was energized, and yeah, now you can't. Well, that was the temperature. The oil, type of liquid, the weight, the model number, serial number, type, and wiring information. Okay? kVA, it's the amount the whole transformer can transform. So if one transformer, the primary is 600 and the secondary is 240, the whole transformer is 500 VA. Meaning the primary is rated for 500 VA, and it equals the secondary, so the secondary is also rated for 500 VA. So it's what the whole transformer can transform in energy from one side to the other. It's not in half. 500 VA on one side. It says 500 VA, primary is 500 VA, secondary is also 500 VA. So that's what it's talking
It's
about.
like you're VAing or whatever. Okay, bars. Just.
Okay? Number of phases, well, if there's 2 wires, it's single phase. If there's 3 wires, it's 3 phase. How's that?
That makes sense.
Yeah. Frequency, be careful of the frequency because of XL equals 2 pi FL.
About,
And what else? That's it. Any questions? I'm trying to get through it with, I did the formulas right away, just to make sure you guys know those. And this polarity thing that's not mentioned in your book, but it is in Learning Task 5. We'll go into it a little more deeply.
How important is the nameplate information?
Really?
So it's gonna be on the class.
All the different categories?
Oh, okay.
Yeah, like
Can
everything.
you name 3 things? I don't know. 3 things.
Yeah.
With manufacturers, phase count?
Sure.
Sure. Just
KVA
manufacturer.
rating,
Manufacturers.
temperature.
number 2.
Model
You
number.
guys can have a look at this if you want. It's got a few things on there, not a lot. It's got a diagram.
Can we hand that around during the quiz?
I'm gonna zoom it in here. Put it on here.
I think I'm gonna go with screws. I wanna work with
Screws on it?
Yeah.
Got a little bit middle in there. Screws.
Okay, what do you think?
You can tighten the screws.
It never feels that bad, but then you're like, oh,